If you've seen the image of an apple falling on Newton's head and believe that you understood gravity, chances are that you couldn't be more wrong. You see, gravity remains one of the most misinterpreted disciplines of science. Although science can measure and predict gravity's effects, what gravity actually is on a subatomic level continues to be one of the greatest unsolved mysteries of our time. Even what we do understand about gravity's characteristics defies conventional expectations. The phenomenon it creates range from the bizarre to the downright fantastical. That gravity is responsible for your perception of time, that's just the tip of the iceberg. The deeper you look, the more you realize that gravity isn't merely weird, it sometimes seems almost magical. As for the ongoing scientific mysteries, we obviously can't provide definitive answers since even the brightest minds in the world haven't cracked the code yet, and we're not up there with them. What we can tell you is that investigating gravity is enough to make you question reality, and perhaps even enough to make you throw away your bloody clock. Gravity is inexplicably weak. Despite being the primary governing force of the universe on a large scale, gravity is almost inconceivably weak. As most are aware, gravity occurs whenever there's an accumulation of mass. The more mass an object has, the stronger its gravitational field becomes. Taking Earth as an example, the gravity produced by our entire planet is remarkably faint. Every time you pick up an object or stand up from a sitting position, you're effectively winning a tug of war against Earth's gravity, and it's not taking much effort at all. Keep in mind that this weak force is generated by a mass of 5.97 septillion kilograms. That's a number with 24 zeros behind it, by the way. On the other hand, Earth's gravity is powerful enough to keep the Moon in orbit, while the Moon's gravity, despite its significantly smaller size, is influential enough to drag the ocean in its wake, creating tides. Tides result from the interplay between Earth's gravity and the Moon's gravity, yet a contradiction remains. Is gravity so weak as to be almost negligible, or so strong that it can shape the entire solar system? In one of its many perplexing characteristics, gravity is both nearly inconceivably weak and at the same time by far the most prevalent force in the known universe. The best way to fully appreciate what gravity is and how it fits into the grand scheme of the cosmos is by comparing it to the other fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Although gravity isn't a force in nature by the same description, we'll get to that particular mind-boggler later. Starting with the strong nuclear force, the strongest in nature by far, it is the force that binds protons and neutrons together. Protons carry a positive electrostatic charge from electrons and are naturally repelled from one another under normal circumstances according to the laws of electromagnetism. However, the strong nuclear force overcomes this natural repulsion, allowing these particles to bind and form more complex structures. On a deeper level, this process is regulated by gluons, which mediate interactions between quarks. Most importantly, for our comparison, the strong nuclear force is about 100 million trillion times stronger than gravity. It's quite strong. Despite its immense strength, though, it only operates on a subatomic scale, having a range limited to the nucleus of an atom. The weak nuclear force is responsible for radioactive decay, playing a major part in both nuclear fission and nuclear fusion. It's mediated by particles called W and Z bosons and is about 1 million times weaker than the strong nuclear force, operating at an even shorter range. Yet, despite even having the word weak in its name, the weak nuclear force is still stronger than gravity by 10 to the 25th power. That's 25 zeros. The last force of nature is electromagnetism, the one that we are most familiar with given its tangible role in our everyday lives. As mentioned earlier, electromagnetism is rooted in the inherent properties of electrons, which are mediated by photons. When harnessed, these forces give rise to modern wonders such as electricity. Although electromagnetism is weaker than the strong nuclear force, it is the only other force that operates on a grand scale, making it highly visible in the physical world. In fact, electromagnetism is stronger than gravity by 10 to the 36th power. If you want a demonstration of just how powerful it can be and the vast scale on which it operates, just take a look at a compass. Regarding its range, electromagnetism shares a rather profound characteristic with gravity, but we'll refer to that in just a moment. Now, getting back to gravity, consider everything that we've discussed so far, keeping in mind how much weaker gravity is than every other force of nature. And now appreciate that it is the force responsible for creating galaxies, forming solar systems, and ultimately governing life as it exists on Earth. Without gravity, it is safe to say that the universe would consist merely of particles floating in a featureless void, lacking any physical structure, and by extension, lacking the natural processes required to create life. A key factor to remember is that although gravity is weak, its effect is unceasing. Over long periods, even the weakest force can produce profound consequences, as demonstrated by the transformation of that featureless void into the intricate universe that we see today. It all began with singular particles clumping together, which in turn created stronger gravitational forces that dragged in more mass. This endless cycle ultimately allowed for the formation of stars, planets, solar systems, and galaxies. It all took an unimaginably long period of time, or at least unimaginably long from a human perspective. We're the ones doing the imagining. The shaping of the universe is ongoing as we speak. If you think of gravity as an invisible force identifiable only by its effects in your physical world, you might be surprised to learn that gravity's fingerprints are visible on every level of the universe. From protostars on their journey to becoming full-fledged stars, to the contours of black holes, to the very structure of galaxies and solar systems. Despite being almost inconceivably weak, there is simply no escaping gravity or defying its effects. That said, you might be struggling to understand how gravity operates on both extremely small and vast scales, especially knowing that the same rules govern both planets and entire galaxies. So there's another mind-bending aspect of gravity to consider. Like electromagnetism, its reach is, by all accounts, infinite. So there's a frequently drawn comparison between the words of fictional Jedi Master Obi-Wan Kenobi and the real description of gravity. Obi-Wan explains that the Force is, quote, an energy field created by all living things. It surrounds us, it penetrates us, it binds the galaxy together. If you replace all living things with all objects with mass, well, you have a remarkably fitting description of gravity. While Obi-Wan never specified the reach of the Force, one can only assume that, like gravity, its influence is boundless. Now, it's incredibly difficult to grasp the concept of infinity. Most people tend to dismiss it as a fantastical idea, since very few things in reality have no limit. Yet the range of gravity is, for all intents and purposes, described as extending to infinity. This means that every object with mass exerts a gravitational effect on every other object with mass across the known universe. When viewed on this scale, it is truly mind-boggling to comprehend just how powerful gravity is and how fundamental it is in the structure of every object in existence. That being said, a bit more explanation is required. A key factor to consider is that gravity, like everything else in the known universe, cannot travel faster than the speed of light. Furthermore, the strength of gravity decreases exponentially the further we move from the body of mass. Although its reach may technically be infinite, the overall effect of gravity becomes almost non-existent at a certain distance. As far as speed is concerned, it's well documented that both the light from the sun and gravity travel at the same speed, arriving at Earth in around 8 minutes. Taking this into account, the gravitational influence of any mass will only travel a set distance in its lifetime, and it's important to remember that bodies of mass tend not to simply vanish, but instead transform into different forms. Regarding strength, gravity operates based on an inverse square law, meaning that the gravitational pull weakens in proportion to the square of the distance. In simpler terms, every time you double the distance from a mass, the overall strength of the gravity it produces drops off by a factor of 4. When this principle is applied across the vast distances of the universe, the force never truly reaches zero. However, it eventually becomes so minuscule as to be just negligible. To look at it another way, it's the biggest body of mass in any given location that has the most tangible effect, overcoming smaller nearby bodies of lesser mass as well as larger bodies that are further away. It is, according to these rules, that galaxies and solar systems take shape regardless of each individual field of gravity having a limitless range. Now, if at this point you're wondering what effect the gravity of your body has on other humans, or what effect it might have on the universe at large, consider that although your body does produce gravity, the effect is virtually immeasurable. We can estimate this effect based on established formulas. The gravitational pull between a body and an identical body, assuming you're 100 kilograms, all right then, equates to 0.0000000417113 newtons. This number is then reduced by a factor of 4 with every doubling of distance, reminding us once again just how negligible gravity is in most cases. Though there is another effect that your body and all objects with mass experience, and this topic will officially transition us from viewing gravity as merely peculiar to considering it downright bizarre. We are, of course, talking about time dilation, an effect that most acknowledge exists, yet one that is often fundamentally misunderstood. It turns out that we all experience time as moving slower or faster depending on various factors, from our location on the planet to our speed at any given moment. In fact, once you fully grasp time dilation and its underlying mechanics, it may dawn on you that the very notion of keeping time is, technically speaking, completely meaningless. Gravitational time dilation. Now, time dilation, fairly straightforward in principle, summarized by Einstein's well-known theories of general relativity and special relativity. Referring to general relativity and taking into account everything that we've just discussed, the phenomenon is best explained as time moving more slowly the closer you are to the center of a mass, at least according to the observer. As gravity weakens with increased distance from the central mass, the corresponding time dilation effect diminishes and time appears to pass more quickly. Therefore, as is relevant to us, time is experienced slowest on the surface of the Earth, while those further away from the Earth's gravity perceive time a little faster. Or at least, that's the way most understand time dilation, although it's a bit more complicated than that. We've just discussed how all bodies with mass produce gravity and affect other masses, even if that effect is minuscule. Additionally, Earth's surface is not completely uniform. Since gravity is based on a body's center of mass, the effect of Earth's gravity also varies depending on where you are. In essence, we are all experiencing slightly different gravitational forces, which means that each of us experiences time at a different rate. The basic formula is that for every kilometer away from the center of the Earth, a clock will record a 24-hour period as being roughly 10 nanoseconds longer. In other words, a person on a mountain peak experiences time slightly faster than someone at sea level, and this difference applies similarly to all levels of altitude, whether below or above. If we extend this reasoning out to further distances, such as the orbit of space stations and satellites, it would seem logical to assume that astronauts are experiencing time even faster. However, that's not the case. In fact, astronauts on the International Space Station actually experience time a little slower, since time dilation is also a characteristic of velocity, and we understand it gets a little bit confusing. At this point, we're examining the difference between general relativity, which deals with gravity, and special relativity, which deals with velocity. Given that the space station travels at 7,700 meters per second relative to stationary points on Earth, velocity time dilation outweighs gravitational time dilation. As a result, astronauts on the International Space Station actually lose time, approximately 0.007 seconds over a 6-month period at that speed and altitude. So yes, we are discussing time differences on an entirely inconsequential level, not something that humans would ever notice or care about. However, the fact remains that the difference is more than zero, meaning that it will eventually accumulate to a tangible amount over a sufficiently long period. A perfect example is that the Earth's core is, over the course of the planet's 4.5 billion years, about 2.5 years younger than the surface. Much more tangible is the effect of time dilation on satellites, even though in many cases the effect isn't particularly significant or meaningful. Yet there is one type of satellite that is specifically designed with time dilation in mind: GPS satellites. Referring back to those astronauts on the ISS, a GPS satellite, like them, is subject to both general and special relativity. It orbits at an average altitude of about 20,000 kilometers and travels at a velocity of around 22,000 kilometers an hour. With the two relativistic forces counteracting one another, a GPS satellite gains roughly 38 microseconds per day relative to a clock on the surface. For context, microseconds are measured as a millionth of a second. However, since GPS operates based on measuring the time it takes for signals to travel back and forth, even the slightest desynchronization can eventually lead to massive miscalculations. It's for this reason that GPS satellites have sophisticated built-in error correction systems to account for time dilation, demonstrating just how big an impact even fractions of a second can have. Now, at around this time, we should refer back to our earlier comparisons with electromagnetism and the other forces of nature to clear something up. Although gravity is often listed alongside these forces, the truth is that it shouldn't be on the list at all. If it wasn't already obvious, gravity operates in a fundamentally different way. It isn't a force in the same sense as electromagnetism, but rather a warping of space-time itself. This warping effect is so profound that it not only alters our perception of time, but can also bend light, even though light has no mass. And on that note, it's time we progressed from merely considering gravity as bizarre to recognizing it as bordering on the fantastical. Gravity is not a force. The effects of gravity, they're often visualized by placing a bowling ball on a rubber sheet, with the bowling ball representing Earth and the rubber sheet representing space-time. This demonstration serves as a useful and intriguing visual aid, though it can be somewhat misleading. It fails to properly convey that objects with mass do not merely create an indentation on a flat surface, rather they wrap or warp space-time around themselves. This warping is what makes gravity so peculiar and distinct from the other forces of nature, placing it in a category all on its own. In addition to causing time dilation, the warping of space-time influences the paths of moving objects, including light. Anyone familiar with light knows that it typically prefers to travel in a straight line. However, light can be redirected by physical media such as water or lenses in a phenomenon collectively known as refraction, altering its direction as it follows the contours of the warped space-time. In the case of gravity, light changes direction not by interacting with a physical medium, but because of the curvature of space-time itself. Thus, even though light has no mass, it is still subject to the pull of gravity. And when you stop to really think about that, the idea is kind of enough to melt even the sturdiest of minds. If you are hoping for a visual demonstration of light conforming to gravitational curves, the bad news is that the effect of the Earth on the Sun's light is so minor that it's not observable. The good news is that you can technically see the phenomenon in action, but only by turning your attention to astral bodies much further away and relying on extremely powerful telescopes. Gravitational lensing, also referred to as Einstein rings, has been observed when a distant light source passes behind an enormous concentration of gravity, such as that of a galaxy. When the observer is positioned at the right angle, with the light traveling directly to their eye, they witness the light bending and warping into a ring as the light source passes behind the concentrated gravitational mass. As amazing as this example is, it pales in comparison to the most terrifying manifestation of gravity in the known universe, the aptly named black hole. It's often said that even light can't escape a black hole, and now you probably get why. While a planet's gravity is enough to deflect light, the gravity of a black hole creates an inescapable well of curved space-time. What actually happens to light inside a black hole remains hotly debated. When too much gravity is concentrated in one place at one time, even the brightest minds on Earth can't fully explain its effects on space-time. And speaking of brilliant minds being baffled, it's time to move from a level of gravity that is merely fantastical to one that we truly do not understand as we continue to grapple with finding answers. Gravity makes no sense on the quantum level. Once again, when comparing gravity to the other forces of nature, and considering that gravity isn't a traditional force but rather a warping of space-time, we reach a point where general relativity stops making sense. On the grand scale, gravity is a tangible and measurable characteristic of space-time, and everything operates in perfect accordance with the established theory of relativity. However, when you zoom in and attempt to quantize gravity at a subatomic level, you quickly find that nothing behaves as expected. Quantizing electromagnetism, the weak nuclear force and the strong nuclear force, is a consistent process. Each of these forces has corresponding particles that mediate their effects in a predictable fashion, even if the exact positions of the particles themselves aren't necessarily predictable at the quantum level. Gravity, in contrast, lacks any corresponding particles, at least none that have been observed, which, no matter how you examine it, defies everything we understand about the universe. The bottom line is that to quantize gravity at the subatomic level, we would also have to quantize space-time itself rather than simply viewing it as the canvas that physics happens to be on top of. Doing so would quite simply produce paradoxes that could eventually collapse our entire model of physics. It's no surprise, then, that what gravity really is and how it functions on the quantum level remains one of the most prominent scientific mysteries today. This is not to say that the global science community is not working tirelessly on the problem or that potential solutions have not yet been put forward. Some of the most prominent hypothetical solutions include the proposed graviton particle string theory and quantum loop theory. The graviton is the missing particle that mediates gravity, and its existence would dramatically simplify our current confusion by aligning gravity with the other forces. At present, however, this particle remains strictly hypothetical, with no confirmed evidence of its existence. Now, we don't have time to explore the complex layers of string and quantum loop theory in detail, but it's safe to say that although supporters exist for both, they too remain hypothetical and are far from being universally accepted as definitive answers. Regarding how far we are from that definitive answer, that's really hard to say. Some in the scientific community now suggest that quantizing gravity might be impossible. Instead, it is proposed that to fully understand gravity, we may need to develop an entirely new model of physics, one that seamlessly combines the grand scale with quantum scale into a comprehensive, all-encompassing hybrid system. Jonathan Oppenheim, based at University College London, is developing just such a theory, one he believes could revolutionize physics as a whole. He argues that unifying concepts traditionally regarded as connected yet fundamentally separate is the way forward. According to Oppenheim, my best guess is that the next theory of gravity will be something that is neither completely classical nor completely quantum, but something else entirely. Physicists are only ever coming up with models that approximate nature, but as an attempt at a closer approximation, my students and I constructed a fully consistent theory in which quantum systems and classical spacetime interact. We just had to modify quantum theory slightly and modify classical general relativity slightly to allow for the breakdown of predictability that is required. Oppenheim's proposals aren't widely supported, but considering that much of the scientific community is still scrambling to account for paradoxes and broken equations, it doesn't seem far-fetched that an entirely new model of the world we live in could offer the answer. In the meantime, take solace in the fact that as confusing as the realities of gravity may be to you or me, they're just as baffling to the smartest people on the planet, at least for the time being. Thanks for watching.